Hi everyone, I'm excited to present our work, Darwin, a flexible learning-based CDN caching system. This is joint work with collaborators from UT Austin, UC Berkeley, UMass Amherst, and Akamai. Content delivery networks serve most of the internet traffic today. They deploy numerous edge servers that are close to the users. Each server acts as a cache for faster data retrieval. Effective cache management policies play an important role in enhancing user experience and optimizing operational costs. However, crafting cache management policy is challenging, given the dynamic nature of CDN traffic. Consider a server that primarily serves download requests of large objects. When some breaking news occur, triggering increasing user demand for related web pages, the same server may start serving the small web objects with high request rate. These traffic changes could happen pretty often in a day. This raises a question: are static cache management policies effective? In this work, we focus on the hot object cache omission policy. In the two-level cache server, objects are first written to a larger but slower disk cache. Those meeting the hot omission policy criteria are omitted to the smaller but faster hawk. A common hawk omission policy considers the frequency and size of the object. It omits an object when requested more than F times, and it has a size smaller than S. An important cache metric that directly reflects the user-perceived response time is the object hit rate. Hawk object hit rate is the number of hawk hits among all the requests. We've observed that static hawk omission policies fall short when faced with shifting workloads. Our analysis of the image and download traffic class subsets of a production server trace reveals that the best policy for one traffic class can be suboptimal for another, resulting in significant performance drops. Given that there is no one-size-fits-all static policy, we pose the question: can we learn the optimal policy for the current traffic? Previous attempts at building adaptive omission policies have their shortcomings. The first problem is some of them restrict the policy decision knobs. Adapt size, for example, only adapts the size threshold. Secondly, these approaches have generally struggled to accommodate hardware-dependent metrics. Methods like hill climbing, which use shadow caches to simulate performance metrics like hit rates, cannot accurately simulate hardware-dependent metrics such as disk ops due to the complexity of modeling heterogeneous hardware behaviors. The last issue is the high overhead. For example, RO cache makes predictions per request, which is significantly expensive. This is where Darwin comes in, a solution that adapts unrestricted knobs, accommodates hardware-dependent metrics with low overhead. Darwin operates on the frequency and size-based hawk omission policies. It evaluates the performance of various policies empirically and selects the best one for deployment until traffic patterns shift. This process presents two challenges: scalable performance observation and efficient policy selection. For performance observation, the straightforward approach is to run each policy for a round and observe its performance. However, this method is impractical with a substantial number of policies, as it takes too many observation rounds. Each round requires sufficient requests to measure the performance of the deployed policy. These observation rounds may not conclude before the traffic changes. With more resources, we can use shadow caches. They serve as a means to simulate the cache behaviors of all non-deployed policies concurrently, but they bring in significant compute and memory overhead. We propose cross-policy prediction models that leverage the shared structure across policies to infer the policy performance correlations. For example, for the request trace shown here, both policy I and J will omit all the red requests with sizes smaller than 50. And policy J would additionally omit the yellow requests whose sizes are between 50 and 100. Under similar traffic, the impact of parameter changes in the policy tends to be stable. The prediction models use traffic features and the performance of one policy to predict the performance of another. We empirically find single-layer fully connected neural networks are effective enough to predict policy relative performance. Given the large number of potential policies, can we further reduce the policy space? We introduce feature clustering and policy association. We extract features from the current traffic and find the closest cluster of the features. Each cluster is labeled with good performing policies for traffic in this cluster. We only need to explore the corresponding policies of the cluster that the traffic belongs to, which greatly reduces the number of policies explored. The second challenge is efficient policy selection. We've developed an algorithm, track and stop with site info, which is a variant of the best arm identification embedded algorithms. Here's how it works. In each round, we observe the performance of the current deployed policy. We feed the observed performance and the traffic feature into the prediction models to predict the other policy's performance. We then check our confidence in the policy performance. If we're still underconfident, it will deploy the next policy to gather confidence and start the next round. If you're already confident, then it will deploy the best policy for future rounds and terminate the selection algorithm. We've theoretically proved that convergence time is bounded by a constant that is independent of the number of policies. Putting it all together, Darwin trains the cross-policy predictors and feature clusters offline. During online policy selection, Darwin first reduces the policies to explore from the feature cluster labels, and then run the track and stop with site info algorithm to deploy the best policy. The cross-policy predictors don't pose limitations on the decision knobs. Because the predictors and because the predictions rely on offline observed policy performance, Darwin can take in account of hardware-dependent metrics. Cross-policy predictors impose lightweight predictions only in the first few rounds. When coupled with the feature clustering, the overhead of policy exploration is greatly reduced. We evaluated Darwin extensively, both in simulations and through an Apache traffic server-based prototype. We checked hot cache size from 100 to 500 MB. We trained and tested with CDN traces of 100 mixed configurations for 2 traffic classes. Our baselines include static policies, a depth size, percentile, and hill climbing. Our results show that Darwin is robust to traffic changes. On the x-axis is the various baselines we compare with, and each bar shows the average improvement in Darwin's hot hit rate relative to the respective baseline. Darwin outperforms the static baselines because no static policy works well in all traces. For the 3 adaptive baselines listed here, percentile uses nth percentile values as threshold. Hill climbing runs 2 shadow caches with opposite directions of threshold changes for each threshold, and moves toward the direction with better performance on each update. A depth size uses Markov chain tuning of a probabilistic size threshold. These methods all require some additional parameter tuning, and they have access to finer granularity of policies. In this plot, we show the baseline results with their best parameters. Despite these advantages, Darwin outperforms all of them. We want to highlight 3 additional results. Firstly, our cross-policy models are robust. Secondly, Darwin can be used to improve other metrics, for example, for a combined metric of hit rate and disk write. Lastly, it doesn't impose additional latency overhead and minimally impacts CPU and memory utilization. Please refer to the paper for more details. To conclude, Darwin can learn the best CDN hot emission policy flexibly with cross-policy prediction models, feature clustering and policy association, and track and stop with site info algorithm. Darwin outperforms the state-of-the-art emission policies with respect to multiple metrics, adding minimal overhead. Thank you for your attention.